Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where we are discussing concepts, chapter wise concepts. Also every day 9 p.m. there will be a video on physics. This video can be of a concept or previous year question paper discussion that we are going to start very soon. So what we are doing chapter wise concept discussion, also chapter wise previous year question paper discussion. So every day 9 p.m. sharp on Diksha Karnataka. Now every Sunday 10 a.m. we will be giving you a test paper on our WhatsApp channel. For that you have to join our WhatsApp channel, and the link will be given in the description below. Now you have to join our WhatsApp group if you are preparing for KCET 2025 exam. Also the question paper that we are giving at 10 a.m. the solutions will be given 8 p.m. on Sunday. So you will get almost 12 hours, 10 hours to solve that question paper and verify the answers in that video. Also you can mention in the comment whatever doubts that you may have while solving that question paper, and we can discuss on that too. Now let us start with today's concept. We are discussing electrostatic potential and capacitance part 1. Today this is video number 3. We have already completed electric field and electric charges chapter. So if you have not seen that, that is covered in 2 parts, video 1 and video 2. Today is video number 3. So we are discussing electric potential. We will mainly discuss about electric potential today. So let's see what all we are going to discuss in today's content. First we are going to discuss about introduction, basic introduction about potential. Then we will discuss about electrostatic potential energy. We will start with electrostatic potential energy. Okay, then we will go to electrostatic potential, and later on in our part 2 we will discuss again electric potential energy. So first we are started with electrostatic potential energy. We will try to understand the meaning, and then we will come back to electrostatic potential energy again in our later part. So don't worry if your concepts, your questions, your queries are not getting cleared in this video. We will come back again and we will try to clear as much as questions, as much queries that you might have while studying the chapter. We will try to clear everything. Okay. Next we will study about potential due to a point charge. Then we will study about potential due to electric dipole, very important. And then we will study about potential due to a system of charges. We have done electric field due to system of charges, electric force due to system of charges. Now it is time for the potential. Okay, so why potential go away? That will also be system of charges, right? Now what is this picture? Tell me. So here it is, water is being released from a dam. Okay, the dam stored some energy, some water, and that is being released through this system. And here is a hydroelectric power plant where this potential energy, stored potential energy, is being converted into electric energy. Okay, so what is the meaning of potential energy? Potential energy is something that is conserved. So basically you can store that and you can use that for later use. That is the basic meaning of potential. So work done against a conservative force is stored as potential energy. So let us understand, here we are doing work against gravity by storing that water at some height. Okay, so work done. We are not doing the work, obviously. Here nature itself is doing the work by storing that, taking that water from the ground level, making it vapor, and then in terms of rain it is falling down from the sky, and then it is stored in a higher place, and that water is released through the dam in a controlled way so that we can convert it into electric energy, right? So the energy stored in this water is potential energy. And why it is potential energy? Because it is achieved by doing work against a conservative force. If you do some work against something, then you are expecting that to be stored, right? For example, if you store some money in the bank, Okay, you want that money to stay there, right? So that means you are storing that money and bank is doing some work and that work is being paid to you in a form of interest, right? Here we are doing physical work and that work has to be stored. Not all forces are conservative. For example, friction is not conservative. Whatever work you do against friction, that work does not store and you do not get back that energy. So if the force is conservative, then you can do some work and that work is being stored. For example, gravity is a conservative force where you do work, that work is stored in form of potential energy. Similarly, electrical forces is also conservative. So if you do some work against electrical force, that also gets conserved and you get back that work. Now here we have a charge plus q, here we have another charge small q. Let's say this charge is negative and this charge is positive. Okay, let's take these charges like this. Now if you keep these charges like this, what will happen? This negative charge will start attracting this charge towards it, so it will feel a force towards the negative charge, right? Now if you try to pull this charge away from this minus q, that is, if you try to move this charge from point A or first point to the second point, point B, if you try to move them in this direction, then what you have to do? You have to do some external work, right? Now that external work, to do some external work, you have to apply some external force, and that work that you are doing to move the charge from point A to point B, that work is gonna store inside. Okay, remember this, when we are using F external, the work done is positive. Now if you are using same thing, if you are using the internal force, what is the internal force? Internal force is the Coulomb force, right? Coulomb force. When you are using Coulomb force, that is K Q by R square. I am just using the magnitude. So if you are using this force, then if you are writing the same work done, okay, then it will be, if you write the same work done, then it will be negative. So there are some cases where you are using the Coulomb force. In that case, this is negative. If you are using the external force, if the external force is given, then this is positive. So basically that means when we are doing work, we are, as an external agent, we are doing work, our work is positive. If the system itself does some work, that is, you are using this charge, this force, then it is negative. Okay, remember this difference. Sometimes we are using positive, sometimes we are using negative. So you may get confused when to use positive, when to use negative. If we are using this equal amount of force as this F, most of the cases this force and this force will be magnitude wise same. But if you are using this force when the system itself is doing work, in that case it is negative. If we are doing work as an external agent, then this work is positive. The work done is against the electrostatic force. So basically what is happening, this electrostatic force, against this force you are trying to pull it and you are doing some work. So that's why it is positive electrostatic force and gets stored at potential energy. This work will be stored inside this charge. Okay, this work will store inside this charge because we are assuming this charge is fixed. This is a fixed charge. Okay, you take this charge, you move it, and once you release that, this charge will again come back, right? That's what is the meaning of stored energy means. Stored energy means when you release it, it will come back to its original position, or even if it will try to come back to closer to the minus q. So that is what meaning of stored energy. Stored energy means this energy is stored inside this charge. Later on it can be used for our own advantage. Okay. Now at every point in the electric field, a particle with charge q possesses a certain electrostatic potential energy. So if there is an electric field, if you have an electric field somewhere, okay, and if you keep a charge q, okay, if you keep a charge q, then this charge will have certain potential energy at each and every point, different values, obviously different values, but it will have a electrostatic potential energy. The work done by the external force increases its potential energy by an amount equal to the potential energy difference between point A and point B. Thus, potential energy difference is given by delta U is equal to UB minus UA is equal to WB. So, what is the meaning of that? Suppose we have a charge here, point A, and we want to move it to point B. Okay. If we are doing some external work by moving this charge from point A to point B, then how much work we have done? We have done the work, we already mentioned that work we mentioned as WAB. Okay, so WAB is the work done by us. I think you may not be very able to clearly see it. So let me write it in forward way. Okay, WAB is the work done by us, right? So we have done this much work while moving this charge from point A to point B. Now what is this statement is saying? That at this point it had some potential energy, say UA. Now when it is moved to this point, it has a new potential energy UB, right? So each and every point the charge has separate different potential energy. So at this point the potential energy was UA, at this point potential energy is UB. So whatever work that we have done, that work done is basically the difference in potential energy. So difference in potential energy is the work that is done by us. So most of the cases UB and UA individually is not important, but this work done by us, WAB, that is the difference of potential energy, that is very, very important. Now let's move on. The work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points. So the example I have taken, so suppose this electric field is there and I am moving the charge from point A to point B, okay, and the work done depends only on the initial value and the final value. It does not depend on the path through which it is taken. Okay, so independent of the path taken to go from one point to other, independent of the path taken means if you take it from this point to this point, or this point to this point, or via this path, whatever path you take, that is immaterial, that is not important. Only important thing is the starting point and the ending point. Okay, you see, UB is the final potential energy, UA was initial potential energy, and the difference is our work done. So work done depends only on the final point and initial point, and it does not depend on the path through which it is taken. Okay, this is the fundamental characteristic of conservative force. So in one of the year KCET they have given different paths, and they asked which through which work done is maximum, work done in minimum, or I think they have asked you to find the work done. Okay, so don't get confused depending upon the path. Work done is immaterial. Potential difference, potential energy depends only on the starting and ending point. It does not depend on through which path you have taken. Okay, the actual value of potential energy is not physically significant. It is the only difference of potential energy that is significant. I already told you that actual value of UB and UA is not so important. Only thing that is important is the difference. Okay, delta U is important and WAB, that is the work done, is important. These two are not so important. Okay, next, let us solve the homework problems that we have given in our previous lecture. In previous lecture, I have given you 2 homework problems. Before moving further, let us discuss the homework problem from the previous class. 2 equal and opposite charges of masses m1 and m2 are accelerated in a uniform electric field through the same distance. What is the ratio of their acceleration a1 by a2 if the ratio of their masses is M1 by M2. So this is a little bit off topic. We are talking about electric potential, but this is mostly about electric field. So if you are getting bored towards electric potential, this will, I hope it will lighten the mood. It will help you to change the gear, and then once we come back, you will again start understanding the concepts. So two equal and opposite charges. Okay, two equal and opposite charges means one charge is plus q, suppose another charge is minus q. Okay, and this mass is m1, this mass is m2, and they are accelerated in a uniform electric field. So suppose the electric field is like this. So this mass will move in this direction, whereas this mass will move opposite direction, right? That is the property of the charges, that in electric field, positive charge moves in the direction of electric field and negative charge moves in the opposite direction of electric field. Now what is the force acting on them? Magnitude of force. Magnitude of force will be equal because they have equal masses, equal charges, right? So force is given by q times E. So electric field, suppose the electric field is E, then the force acting on each of the charges is given by q times E. Now what is the acceleration? Acceleration of mass 1. Acceleration of mass 1 is force divided by m1. That is QE divided by m1. And what is A2? Similarly, it will be QE divided by m2. Now what is A1 by A2 that they have asked you to find? So A1 by A2 is QE by m1 divided by QE divided by m2. That is equals to m2 by m1. Now what is given? m1 by m2 is given. m1 by m2 is given as 0.5, right? m1 by m2 is given as 0.5. So m2 by m1 will be 1 by 0.5, right? That is equals to 2. 1 by 0.5 is equals to 2. These are the shortcut answers that you have to remember by heart, right? So A1 by A2, the value of A1 by A2 is equals to 2. So correct answer is option D. So if you have struggled to solve this problem, or even if you have not even tried to answer that question, please check this solution. Now let's move on to the next question. We always share 2 homework problems after each lecture. Today also I am going to share 2 questions after my lecture is over. You have to answer those 2 questions and mention the answer in the comments below. If your answer is correct, you will get a thumbs up and a reply from us. Okay. Now, an infinite number of point charges. This problem is very interesting problem, especially if you are preparing for KCET, if you are preparing for JEE, if you are preparing for NEET, for all exam, this concept is very important. An infinite number of point charges each equal to q are placed along the x-axis at x equals to 1, x equals to 2, x equals to 4, x equals to 8, ... and so on. The resultant electric field at the origin due to all these charges is 360 volt per meter. So electric field is given. Okay, and then you have to ask what is the value of q. So what is the question? Let's understand the question first. So we have coordinate system, and we have 0, 1, 2, 3, then 4, 5, so on, right? Now each point has a charge q, okay, plus q. Everything is plus q or whatever minus q. Because the electric field is plus, so we can assume this is plus q. Now what else is said? It is said that the total electric field at the origin is 360 volt per meter. Okay, sorry, this is my mistake. I made one small mistake. It is not 3. There is no charge at 3. Okay, 1, 2, 4, then 8. Then 8. So it is a kind of GP series, right? It is a kind of GP series, right, again at some point. Okay. So now what we have to do, we have to find the total potential at this point, okay, and it is continued. Okay, next is 16, 16, after 16, 32, like that. So what is the electric field? We have to apply the concept of superposition principle, that is electric field due to multiple charges. So E1 is KQ by R1 square, that is KQ by 1 square. What is E2? E2 is KQ by 2 square. What is E4? E3 are not here. I am just writing the according to the coordinate, that will be easier to remember. Q by 4 square. Okay, what is E8? KQ by 8 square. So what is the total? Like that it continues for all the charges till infinity, till E infinity. Okay, now what is the total electric field? Total electric field is sum of all the electric fields, that is we have to write KQ, it is common. KQ is there for all the charges, right? KQ is there for all the charges, so it will be 1 by 1 square plus 1 by 2 square plus 1 by 4 square. Okay, now what we have to do, we have to find the sum of this series. So this is basically a mathematical problem, not a physics problem. Now tell me, what is the value of this series? Now this term is a finite term. What we will do, we will take this term out of this series. Okay, so let me rewrite this. So we can write this as E equals to KQ. Okay, 1 KQ is out plus KQ 1 by 2 square plus 1 by 2 square whole square 1 by 2 cube whole square plus 1 by 2 to the power 4 whole square plus so on. Right? Now this is the thing. Now what is the, this is a GP series, right? This is a GP series, infinite GP series, and the common factor is less than 1. So this is a converging series, we know that, right? Now what is the common factor? How can we find the common factor? If you to find the common factor, what you have to do, you have to take any number and divide that by the previous number, right? So let us take that 1 by 2 cube number, 1 by 2 cube whole square divided by 1 by 2 square whole square. So you will get 2 square divided by 2 cube whole square, that is 1 by this 3 and 2 will cancel, it will be 1 by 2 whole square, right? So you will get 1 by 2 square. So the common difference is 1 by 2 square. You can check with any two numbers, after n, okay, you will get 1 by 2 square as common difference. Right? There is a different way of doing it, the same thing in mathematics, but I am not doing that way. You can check 1 by 2 n plus 2n to the power n square plus divided by 2n minus 1 to the power square, you will get the same result. Okay, don't worry about it. Now what is the sum of this all the terms? What is the sum of these all terms? These all terms in the bracket, infinite up to infinity. We know that the sum is given by GP series, sum is given by not A, Sn, sum of all the numbers S infinity is given by A1 divided by 1 minus the common difference, okay, common ratio. So here A1 is 1 by 2 square, A1 is 1 by 2 square, and what is the common ratio? Common ratio is also 1 by 2 square. So 1 minus 1 by 2 square, or 1 by 4 divided by 1 minus 1 by 4. Now what is 1 minus 1 by 4? It is 1 by 4 divided by 3/4, right? 1 minus 1/4 means 3/4. Now take this up, it will become 1 by 4 times 4 by 3. So you will get 1/3, right? So 1/3 is the sum of everything inside this bracket. Okay, now I am removing this part for now, or let me go back to the previous slide and answer the question here. This is the solution, right? So what we are going to do is, we are trying to find the electric field. Electric field is KQ plus KQ times, what is the value we received? We received the entire value of this term as 1/3. So this will be 1/3, right? So KQ is again common, 1 plus 1/3. So it will be KQ times 4 by 3. Now 4 by 3 is, this value is given 360 volt per meter. So this is little bit lengthy question, but don't worry, conceptually this is not super difficult. So 360 times 3 divided by 4. So it is 90. So it is 3 in the 270. That is the value of K times Q. So what is the value of K? So Q is 270 divided by K. Now what is the value of K? Remember that value of K is 9 times 10 to the power of 9, right? So 9 is cancelled, 30, you get 30 times 10 to the power of minus 9, that is 30 nanocoulomb. So 30 nanocoulomb means option is A. Okay. If you have any doubt, mention that in the comment below. So we have already completed our homework. Let's move on to the next concept, electrostatic potential. So electrostatic potential is potential energy per unit charge. So we have done, we have discussing about electrical potential energy. Now we are discussing about potential, similar to that of Coulomb force and electric field. If you remember, Coulomb force was given by K, Q1, Q2, or let us use the same notation that you used our notes. Okay, so KQ by R square. Now what, to define electric field, what we have done, we divide it by one of the charges, right? We divide it with one of the charges and we say electric field is force per unit charge. Similarly, now we are defining electric potential, similar to that of electric field, is potential energy per unit test charge. And remember that electric potential is cousin brother of electric field. We will see the relationship between them. Okay, so don't worry. Similar to that electric force and in a field, now we are relating potential with potential energy. Now you should remember that potential and potential energy, two things are not same. They are obviously related like electric field and Coulomb's force, but they are not directly same. So electric potential is potential energy per unit charge. Unit charge means obviously if we make this charge, 1, okay, if we make this charge 1, then electric field generally becomes force, right? So for electric force per unit charge, similar to that, we can define electric potential, and electric potential is given by delta V. Delta V is delta U by delta Q. So UP minus UR, sorry, UA, we have used the symbol UA and UB. Okay, UA minus UB divided by Q. So if we divide the work done that we have done by the charge that we removed, you remember in our first slide where we moved the charge Q, and if we divide by that charge, then we will get the potential. Potential also denoted using this symbol. Okay, this is the potential of the point P. So we talked about potential energy, right? At point A, UA was potential energy and UB was potential energy another point B. Okay, now when we divide that by Q, we say this is potential. Okay, divided by Q is potential, not potential energy. Okay, so when potential is divided by potential energy, we get the potential. Okay, now when we take this point B to infinity, if we take the point B to infinity, if we take this point far away and towards infinity, we know that the potential at infinity, it is defined, potential energy or potential at infinity is 0, right? So BB as B tends to infinity is equals to 0. Okay. So work done by an external force in bringing a unit positive charge from infinity to a point is the electrostatic potential at that point. So this is the definition, this is the physical definition of electric potential, that when you bring a unit test positive charge from infinity to a point in electric field, whatever work that you are doing, that work is called electric potential. Now remember, this is a hypothetical definition, this is a physical definition. You cannot go to infinity and bring a unit test positive, not always, right? If you want to measure the potential of each and every point, then you are not going to take a unit test positive charge, go to infinity, then come to this point and calculate the work done. Okay, so this is a theoretical definition. Only thing that is important here, that the potential at infinity is 0. That you should remember. Whenever you are encountering potential 0, that means it may be at infinity. Okay, now let's move on. To obtain the work done per unit test charge, we should take an infinitesimally small test charge. So basically what we will do, we want to find the electric potential. Obviously we are not going to go to infinity, we will take a very small test charge. Okay, so say for example 1 electron. Okay, and that charge we are calling dq. Okay, to obtain the work done dw in bringing it from infinity to the point and determine the ratio dw by dq. Okay, so basically what we will do, we will calculate small work done. Okay, in between, somewhere in between infinity and our point, we will calculate small work done dw, and we know the dq, we'll just find the ratio. Okay, don't need to bring it from infinity, we will do something in between. Okay, also the external force at every point of the path is to be taken equal and opposite to the electrostatic force on the test charge at that point. So basically, as I said, whenever we are moving a charge, it has to be equal to the electrostatic force at that point and opposite to that. Okay, so that's why we are saying this work done is positive. Now potential energy and potential are not the same. I mentioned it multiple times. Work done to bring a unit test positive charge from point A to point B is the potential difference between the points. The work done by the external force is positive, then the potential difference is positive. So as I said, if external force, that is us, we, or any external agent is doing work, that means the potential is positive. And if the work done by the external force is negative, that means we are not doing the work, the electric field itself is doing the work. In that case, the potential is negative. For example, when you keep a negative charge in a positive charge, near a positive charge, okay, and you release it, the charge will move automatically. You are not doing any work. The work is being done by the electric field. So if electric field is doing the work, that means we are doing negative work, right? That is the definition of work. Now let us look into the potential due to a point charge. So we have a point charge q over here, and we are trying to find electric potential at this point P, and we are bringing a unit test positive charge from somewhere in infinity, and in between there is a point A and there is a point B. We are trying to move it from A to B by a small distance dx, and this distance is dx and this charge is +1. Then how much work we have to do? That work is the potential energy stored in the charge, and if we calculate by integration, the method, I mean I showed you the method. Okay, we have to calculate dw by dx. Okay, and whatever we are doing, that we have to calculate by using formula, and in this case you can calculate it, the potential energy to be 1 by 4 pi epsilon naught q by r. The derivation is not covered in this series. Derivation will be covered in a separate series aimed for all students. Okay, this is only for KCET student. So we are not very focusing on derivations. We are only focusing on the formulas, outcome of the derivation. So the potential here is given by 1 by 4 pi epsilon naught q by r. Okay. Now, if you remember, the expression for electric field was 1 by 4 pi epsilon naught Q by R square. So if you see, there is only one difference, it was squared, it is R. So if we plot the graph, what will happen? We will get the graph of electric field starting at a higher value but falling very fast. Okay. So because it depends on 1 by R square, it depends on 1 by R square, it falls very fast compared to potential. Okay, potential is dependent on 1 by R. Okay, so it falls slower. But similarly, when the value of R is less, very small value of R, E's value is very high. Okay, so for example, if the distance is 0.01, so in that case 0.01 means it will be 0.01 square inverse, right? So it will be 10 to the power of 4. But in case of potential, it is only 1 by 0.01, that means 10 to the power of 2. So that is also true for lower value of R, E is very high, and for higher value of R, it falls very rapidly. But potential, it's for lower value of R, the value is not that high, but it falls little bit slowly when it goes to infinity. Okay, but at infinity, as we are approaching infinity, both E and V both are 0. You should remember that at infinity, electric field and potential both are 0. Now, potential due to an electric dipole, we have already calculated electric field due to dipole at two different positions. Now, if you calculate the electric potential due to the dipole, say plus minus, potential dipole moment is in this direction, and we are calculating dipole at any angle at some point at an angle theta, then the electric field is given by this formula. Now, this is the expression for electric field on the axis of the dipole, right? You remember electric field on the axis of the dipole. There is a cube here, sorry. There is a cube here. Now, what will be the expression for electric potential on the axis? Potential of the axis will be 1 by 4 pi epsilon naught P by R square, right? This is the expression for potential on the axis. Now, what will be the electric potential at any arbitrary point, say at an angle theta? Okay, at any point, say P at an angle theta, it will be 1 by 4 pi epsilon naught P cos theta by R square. That is the general expression for electric potential on the axis of a dipole, sorry, on the at any point on the dipole. Now, tell me what will be the value of potential on the equatorial plane. This is a homework task. This is the bonus task. You need to answer this question in the comment below. What will be the potential on the equatorial plane? Now, let's move on. Potential due to a system of charges. So, we have different charges, and we want to find the electric potential at this point P. So, what we have to do? We have to do the same method that we have done. We have to calculate the potential due to individual charges. K Q1 by R, V2 is K Q2 by R1. Okay, R2. They have mentioned R1. Then they have given R2P, okay, say 2P, okay, R1P, V3. Now, potential is a scalar quantity, okay, potential is a scalar quantity. So, this is the easier form than electric field. In case of electric field, you don't need to worry, you need to add them in vector form, but here you can simply add the total potential is given by sum of all the potential, okay, sum of all the individual potentials, okay, and this is just scalar addition. And in numericals, in mathematics, in MCQs, it is very common. They will ask you separate, they will give you there is a triangle, okay, what is the electric potential at the center, or there is a rectangle, what is the electric potential at the center, or there is a rectangle, what is the potential at the one of the corner. So, there are different types of varieties where electric potential is very common. They will ask you numerical question based on this. Now, let us solve one of the KCET question, came in 2022. The electric field and potential of an electric dipole along its axis vary with distance r respectively as I said that normally electric field and potential are related like this. So normally electric field is proportional to 1 by r square and normally electric potential is proportional to 1 by r. But for dipole it's a special case. For dipole electric field varies as 1 by r cube and potential is one order less. Remember that potential is always one order less than that of electric field. Okay, so electric field is 1 by r cube, so potential will be 1 by r square. So the correct answer is first one. What is the first one? You have to be careful while answering that. So first is electric field and then is potential. So 1 by r cube and 1 by r square, 1 by r cube and 1 by r square. By mistake, do not answer option A. Option A they have given in the reverse order. So 1 by r square and 1 by r cube. So be careful while answering such questions. Okay. Now let's look into our homework problem. You can get all the homework problem in the PDF that we are going to share as a note. Okay. Or you can take a pause here, write down the question and try to answer them at your free time and mention the answer below in the comment before we are going to upload the next video tomorrow. So don't worry, tomorrow's lecture in between somewhere we are going to provide the answer for these questions as well. So as usual I am going to give you two homework problem. First question is this and next question is this. You can pause the video again and write down the question or solve the question and write down the answer in the comment below. Okay. There is a separate playlist created for our lectures. All the lectures will be available in this playlist and you can see all the videos available to see, and you can check the playlist. Link is given in the description below. Also I request you to join our WhatsApp group where we are going to share all the materials that related to this lecture as well as weekend question paper, weekend test and today's note, homework problem. Everything will be shared in the WhatsApp channel. So please join the WhatsApp channel, and if you are watching our channel, our YouTube channel for the first time, then don't forget to subscribe to our channel. Thank you for watching.